Welcome back. This is the second video in our series. You should have just learned about arithmetic sequences, and now we're going to talk about series, which is when you take all the terms of a sequence and add them together. We're going to start by giving you the formula. We'll use the formula, and then we'll explain it. So that's a little bit backwards instead of starting with a proof. We're just going to start with what it is, and then we'll explain it later. I hope that's okay. So the sum of the first n terms of any arithmetic sequence is given by, we use Sn to indicate, sum, so that's S for sum right there. A1 plus An, so that's the first term, plus the nth term. And, that would be like if I have the 10th term, I'm looking for the 10th sum, so I would use the 10th term there, right? That n has to match everything. N is the number of terms in the sequence that you're adding up. And then 2 is 2. That's the number 2. So you take the first term plus the nth term, multiply it by the number of terms, and then divide by 2. And again, we're going to explain why this is in a minute after we do the example. So here we have example, I've called it example 4. 2 plus 4 plus 6 plus 8 plus 10. I picked something that you can probably do on your own, but let's use the formula just to see that it works. That's our first term. That's our nth term. But specifically, it's the last term and it's the 5th term. So that means that n is equal to 5. There's 5 total terms. So the sum of the first 5 terms of this sequence should be given by a1, which is 2, plus a5, which is 10, times the number of terms, 5, all over 2. Okay, so that's 12 times 5 all over 2. Instead of doing 12 times 5, let's do 12 over 2. That's the same as 6 times 5, or 30. So my formula pretty quickly shows me that the answer should be 30. And you can, of course, check that out. We don't even need a calculator for that. You could just do 2 plus 8 is 10, grouping. 4 plus 6 is 10, and 10 is 10. So you have 3 groups, each making 10. That gives you a total sum of 30. So our work seems to be correct. Why does this formula work? Well, the answer actually is that idea of grouping terms, but not grouping terms in the way that I just did it, grouping them in a more orderly way. So let me justify why this formula is the way it is. And again, this is not going to be a full proof. This is just a justification. So I'm going to say this is our sum, would be 2 plus 4 plus 6 plus 8 plus 10. Now, I want to do something sneaky. I'm going to pretend that I don't know the answer is 30, and I'm going to pretend that this is, like a generalized thing, but I'm just using these 5 numbers. I'm going to write a second copy of that sequence, or series, but I'm going to write it backwards. Maybe I'll call it Sn prime. I don't know. You can call it 10 plus 8 plus 6, nope, yes, plus 4 plus 2. And now I'm going to add. I can do that, right? You're allowed to reverse the order of something. That doesn't change the addition. It's commutative. Now I'm going to take my 2 copies and add them straight down. So I get 2 Sn, and it doesn't matter that this one was backwards and that one was forwards. It's still the same sequence. And this is 2 plus 10 is 12. 4 plus 8 is 12. 6 plus 6 is 12. 8 plus 4 is 12. And 10 plus 2 is 12. Whoa. Oh, interesting. So wait. So here, how many 12s do I have? Well, I have 5 of them. And because they're all the same number now, I can just write this as 5 times 12. And that was equal to 2 of my sequences. So to find my total sum, my Sn, I can just divide by 2 and get that Sn is 5 times 12 over 2. And that's why we divide by 2. It's also why we multiply by the number of terms. So in the formula, this is the n, that's the number of terms. 12 is the sum, a1 plus an, the first and last. And 2 is there because we had 2 copies of the sequence and we divided it down. If you did this with the general sequence, and it's not a terrible proof to do, and I'm not going to do it here, it all works out the same way, and you get the generalized arithmetic formula. But it's really important to recognize that this only works because these have that constant common difference of +2 the whole time, so that when you reverse the sequence, the difference maintains and works the same way. Another way to think about this sequence, and like this is the way I like to think about it. Another way to think about this formula is that you're doing a1 plus an, and then dividing it by 2. That's basically saying what the average term of a sequence is. You say, hey, okay, I know kind of what the average term is because I know what the first plus last divided by 2 will be. That should be like the middle term, and because it's arithmetic, it's regularly increasing. That should give me effectively the midpoint, if you think about it like a line. If I know what the average term is, then I just need to multiply it by the number of terms. And that should tell you the total sum. So those are two different ways to think about proving or justifying this formula without going through a rigorous proof. Either using 2 copies of the sequence or thinking about the average term. But really all you need is the formula here. Yeah. Let's do some more examples. So once you have a formula, just kind of like with the arithmetic sequences, you can use the formula in a lot of cool ways. All right, so this is going to be an example where we find the sum, but we have to find out some more information about the sequence first. So I'm asked to find the sum of 16 plus 9 plus 2 minus 5 minus 12 ... minus 75. And this is a little weird at first because I see that there's, it's plus 9 plus 2 and switches to minus. But one thing is we can think about this as really plus -5 plus -12, etc. So this really is an arithmetic sequence or a series. We're adding up a bunch of terms, even if some of them are positive and some of them are negative. We should probably check and make sure it's an arithmetic sequence also. So we could do 9 minus 16, consecutive terms subtracted, that is -7. We could do 2 minus 9, that is also -7. -5 minus 2, that's also -7. So, at least for the first 4 terms, this difference appears to be -7. So I do know the common difference. All right. Now, I want to find the sum, though. So, I remember the formula for the sum is a1 plus an times the number of terms and divided by 2. Now, what do I know here? Well, I know that a1 is 16, and I know an is -75. So 16 minus 75 times n divided by 2. But now I'm running into a problem. I don't know how many terms are in this sequence. That's currently unknown because it's hiding in that little ellipses. So to find n, we need to write the equation of the sequence itself, not of the sum, but of the sequence. And that sometimes happens in the middle of a problem, is you learn, well, shoot, we need to go find some more information and come back before we can solve the problem that I really wanted to solve. So I'm going to put a big star by this. We're going to come back to you. And instead, we just need to write out the terms, not of the sum, but of the arithmetic sequence. So the arithmetic sequence is an is a1 plus n minus 1 times the difference. And now we know some stuff. I need to know n when an is 75. So I can do negative 75. So -75 is equal to 16 plus n minus 1 times the difference, which we found earlier to be -7. And if we hadn't already found it, this would be the time when you would go find the difference by subtracting some consecutive terms. Now it's just algebra. We have everything except n, which is what we need up there. So let's solve for it. Divide by -7, we get 13 is equal to n minus 1. So 14 is n. That means there are 14 terms in this sequence. When you start at 16, it takes 14 terms to get down to -75. You can also then use this fact in that space. So our final sum should be 16 minus 75 times 14 over 2. Buttons are hard. I don't know why I couldn't get that to work, so I'll just do it on here. 16 minus 75 times 14 is negative 826 divided by 2 is negative 413. That seems like an awfully small number, but let's just do a little, sanity check. We only have 3 positive terms, and we have a bunch of negative terms, and we're adding them all up. The smallest is negative 75, so it does make sense that the answer is going to be pretty small. Negative 413 is the sum of all of these numbers. All right, let's take a look at a similar problem. This one's going to use our friend sigma notation. So remember, when you see this guy, it's asking you to take a bunch of terms and add them up. That's what we're doing in this section on arithmetic series, is adding up a bunch of terms. So when you see this sigma, you should immediately be thinking, I bet I need to use maybe one of these formulas. First plus last times number of terms divided by 2. It's easy to remember. All right, well, so I need to know 3 things. I need to know the first term, the last term, and the number of terms. Now, we could write out every term. The way you write out terms here is you just let I equal 1, because that's the lower index of summation. And then we do 9 times 1 minus 12, which is negative 3. So that's the first term. And then we could let I equal 8. That's the upper index of summation. So 9 times 8 minus 12. 9 times 8 is 72. Conveniently minus 12, that's 60. That would be A8, or the 8th term. One really nice thing about sigma notation, at least when your index is 1, is that this tells you that there's 8 terms. Because we started at 1, we went up to 8. Now, it won't always start at 1, so you do have to be a little careful. You can't just read the number on top. But at least in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 terms. So n is equal to 8. And actually, everything we need is already here. So to find this sum, the first of the first 8 terms, we do negative 3 plus 60 times 8 and divide that by 2. I did get my calculator working. That's 57 times the number of terms times the number of terms. That's pretty big. We divide that by 2 and we get 228. And again, that seems like a lot, but remember, we're adding up a lot of terms. The biggest term is 60. The term before that would have been in the 40s, so it's going to grow pretty quickly. 228 is our sum. And we didn't have to write out all the terms of the sigma notation, and we could, of course. We know the difference is 9. So it would be, negative 3 plus 6 plus 15 plus... skip a couple steps, right? The sigma would have been saying do this, which you could have just done, but it sure is a lot easier to just use the formula if you know you're working with an arithmetic series. We're going to close the video by looking at 2 non-examples of times when you can't use this lovely arithmetic series formula. So the first one is the sum from k equals 1 to 4 of k squared minus 3. And this time I am going to actually just write it out. So this would be saying, all right, when k is 1, 1 squared minus 3 is negative 2. And when k is 2, that would be 4 minus 3, or 1. When k is 3, that would be 9 minus 3, or 6. And when k is 4, that would be 16 minus 3, which is 13. So I would be doing negative 2 plus 1 plus 6 plus 13. And you might say, okay, well, I know there's 4 terms. I know the first term, I know the last term, I know to divide by 2, etc. But there's a problem. That problem comes from this k squared. This is not an arithmetic sequence. So don't get, so excited to use your formula that you forget that there's a requirement. You've got to be looking at an arithmetic sequence. So the difference from -2 to 1 is a plus 3. But from 1 to 6, oh no, that's a plus 5. And from 6 to 13, oh, that's not even a plus 5. That is a plus 7 to go from 6 to 13. And maybe it appears to be like a pattern in the differences, but it's not a constant common difference. So you can't use the arithmetic series formula. The best thing you can do in a case like this where you have an exponent, it's not linear, is just add the terms up the long way, or use your calculator. In this case, it comes out you get 18, and I guess if you run into it, you could check and attempt the arithmetic formula, and you wouldn't get 18. I'm pretty sure you'd get 11 times 4 over 2, which would be 22. That's wrong. That doesn't work. So the formula here has failed us because this wasn't arithmetic. All right, and then the final thing you might see is a sum that is called an infinite sum, right? So we can't have an infinite arithmetic series. You can just have the terms go on for forever. When you start to talk about adding them up, it might not make sense to do this. So, right, if you interpret the sigma notation, the sum from I equals 1 to infinity of 2i minus 1, well, this is just going to be 2 times 1 minus 1 is 1, 2 times 2 minus 1 is 3. This is going to be the sum of all the odd integers. 1 plus 3 plus 5 plus 7 plus 9 plus... But the problem is it grows all the way down. And you could, if you chopped this sequence off and said, all right, stop here, you could absolutely find the sum. You could find what's called the partial sum of the infinite sequence. But you can't find the infinite sum because the terms keep growing. So there's no way that a sum of an infinite number of terms that keep growing and growing and growing is ever going to approach or reach anything other than, I guess, infinity itself. So, I guess you would say that this is just equal to infinity itself. But it's weird to say that something's equal to infinity, so we would probably just say, instead of writing that, we would just say this series diverges. Diverges means that it does not converge to a single specific value. It just keeps on growing and growing and growing. So you probably won't be asked to evaluate these, but it just, if you're writing sigma notation, you see stuff, and it comes up that you have something that's growing like this, it's not going to converge to a single value. We'll say this is a divergent infinite series. And it is true 100% that an infinite arithmetic sum will never converge to a finite value. So if you see you have an infinite sum and you can see that you have something that looks arithmetic, like you have a difference of 2, you're never going to converge. It's never going to line up. But hopefully the way I've phrased that is making you think a little bit like, could there be some other types of infinite sums that do converge to a finite value? And I'd like you to really think carefully about that just as a question, and maybe you'll come back to it in a day or two and find out the answer. All right, so we've closed with 2 non-examples of either things that are too big to evaluate or not arithmetic to evaluate. But let's just conclude and go back to what we'd learned today. 1, arithmetic sequences have a constant common difference. They act like linear equations or linear sequences. They grow at a regular rate, and you can always predict how they're going to grow. Because they grow so regularly, they can always be found finding the general term with the equation an is a1 plus n minus 1d. And then if you need to add up the terms of any finite arithmetic sequence, not infinite, you can use the sum of the first and last terms times the number of terms and divided by 2. With these 2 equations and this general definition of arithmetic sequences, you can do any problem in the book. Now, I will say that the problems we've done today have been probably pretty basic. They can get more complicated. There's problems where you don't know the first term, you know, maybe the third term and the seventh term. You can still make it work. So if you're ever stuck, just make sure you list your givens, list what you need to know, write out the formulas, use your formulas to find what you need. You will always get a solution. Just be persistent. Every problem can be a little different, but you can do it. All right. Thank you all for watching. Let me know what questions you have, and I'll see you all next time.